This video will look at angles on the Cartesian plane with angles in radians. So as a review, you've already done angles on the Cartesian plane using degrees. So as a review, an angle in standard position is considered to be an angle that's measured from the positive x-axis, and then the terminal arm for that angle is rotated away from that positive x-axis. If that angle is rotated in a counterclockwise direction, it's known as a positive angle. And if the angle is rotated in a clockwise direction, then that makes a negative angle. Okay, so in this case, here's our angle theta that we say is an angle in standard position. This particular angle has been rotated in a positive direction because it's been rotated counterclockwise, so the opposite direction to a clock, from the positive x-axis. When using the Cartesian plane, we usually divide our plane up into 4 different quadrants. This one being referred to as quadrant 1. That's the quadrant where x and y values are both positive. And then rotating in a positive direction or counterclockwise direction. This was quadrant 2, this one's quadrant 3, and this one is quadrant 4. And we can also label our axes using angle measurements. Now, in previous courses, we may have labeled this using degrees, so 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then back here for a full 360 degrees. Here we're going to be labeling this using radians for the angles. So we're starting out here with 0 radians if we don't rotate away from the positive x-axis at all. That would be an angle of 0. Rotating over to where the 90 degrees would be. In radians, this is pi by 2, and that's because we know 180 degrees is equal to pi, and so 90 degrees has to be half of that, so half pi or pi by 2. And then rotating around here to the negative y-axis, well, that would be pi by 2, 2 pi by 2, this is 3 pi by 2. And rotating all the way around would give us 4 pi by 2 or 2 pi. So the positive x-axis could be referred to as 0 radians or 2 pi radians. Or, for that matter, 4 pi radians if we rotate around twice. Negative 2 pi radians, we could rotate all the way around in the negative direction. All of those would represent this positive x-axis. The related acute angle is the acute angle that the terminal arm makes with the x-axis. Okay, so let's say here's our Cartesian plane, and I draw a terminal arm here, meaning that my principal angle has been rotated around here. Then the related acute angle is the angle the terminal arm makes with the x-axis. That would be this angle here. And notice that it's always going to be an acute angle. So it's the closest x-axis that we're looking at here. So that would be our related acute angle, which is often given the Greek letter beta. A coterminal angle is an equivalent angle that we can create by either rotating around multiple times or by rotating in a negative direction. So as an example, an angle of 2 pi, so rotating all the way around and coming back to the starting position, that would be a coterminal angle for an angle of 0 radians. Okay, here's the first example. Given the angle 5 pi by 4, determine a coterminal angle. Now it just says determine a coterminal angle, and so we have some options here because there's multiple coterminal angles for a particular angle. Let's start by drawing this angle on our Cartesian plane. Now here, we're looking at 5 pi by 4 radians. So what we want to start with is splitting pi into 4 sections. And we know we have 5 of those sections. So if we split pi into 4 sections, well, pi is 180 degrees, so pi is here. If we split pi into 4 sections, we're going to have 2 sections here and 2 sections in quadrant 2. If we split the bottom half of the Cartesian plane into 4 sections as well, because this is another pi radians, okay, what we want to do to get the angle 5 pi by 4 is rotate 5 of these quarter sections, right? So pi by 4 is what we've done here. We've split pi into 4 pieces. We want 5 of those pieces. So 1, 2, 3, 4, 5. So 5 pi by 4 will be this angle. Now, because of the way our Cartesian plane has been split up, we already know that the related acute angle has to be pi by 4 because it's 1/4 of what pi radians would be. Now, coterminal angles for the angle theta would be theta plus, or minus potentially, some multiple of 2 pi, right? Because if I take my angle theta and add 2 pi to it, it just means that I'm rotating around an extra time, but I would still come back to the exact same position on the Cartesian plane. So if I multiply 2 pi by some number, by some integer, and add that to my original principal angle, 5 pi by 4, I'm going to get another angle that is coterminal to the original. Okay, so this is for n values that are integers. So this fancy z represents the set of integer numbers. So a coterminal angle for 5 pi by 4, one possibility would be starting with the original angle and adding 2 pi. Okay, or in other words, using the integer n equals 1. Okay, so this gives us 5 pi by 4. And finding a common denominator here, I know 2 pi is equivalent to 8 pi over 4. And so I get a total of 13 pi by 4. So 13 pi by 4 is a coterminal angle to 5 pi by 4. That's not the only coterminal angle. I can get other coterminal angles by putting in other multiples, so other integer values for n. Let's say, for example, I put in an n value of -1. Okay, well, that would mean we're ending up with a negative angle, but I would take 5 pi by 4. So I would take 5 pi by 4 and subtract 2 pi. So I'm using the n value of -1 now. So that would give me 5 pi by 4 minus 8 pi by 4. That would give me the negative coterminal angle of -3 pi by 4. Okay, so that would be this angle measurement here if I rotated in a negative direction. So -3 pi by 4 is also a coterminal angle to 5 pi by 4. So a coterminal angle means that we're going to end up back at the exact same spot on the Cartesian plane. In order to determine trigonometric ratios for any angle on the Cartesian plane, what we can do is determine those ratios by putting an angle theta in standard position. So let's say I've got a point P with coordinates x, y on a terminal arm. So this would be our angle in standard position, theta. That also means that this would be our acute angle, beta. Trigonometric ratios are defined using a right-angled triangle. So what I'm going to do is I'm going to drop in a vertical line here in order to make a right-angled triangle with the x-axis. Okay. Now, because this point P is x comma y, I know that this base of the triangle is x units. This height of the triangle is y units. And this is defined as r, or in other words, that would be the radius of the circle if I were to rotate point P all the way around in the Cartesian plane. This would be the radius of that circle. Okay. Now, r is defined, or r squared is defined as being x squared plus y squared, simply because of the fact that we've got a right angled triangle here. So that's using Pythagorean theorem. Okay. Now, based on our picture here, if we were to look at the trigonometric ratios for angle beta, so our related acute angle, then sine of beta would be opposite over hypotenuse, so y over r. Cosine of beta would be adjacent over hypotenuse, so x over r. And tangent of beta would be opposite over adjacent, so y over x. Something called the cast rule is something that can help us remember which trigonometric ratios end up being positive or negative in each quadrant. So if you recall, the cast rule starts in quadrant 4, C-A-S-T. Okay? Now, if you'd rather have something to remember this by that starts in quadrant 1, you could make up your own saying that would help you remember ASTC. Sometimes it's easier to remember starting in quadrant 1 rather than starting in quadrant 4. So one possibility that I told my grade 11s last year, you could use all schools torture children. Okay, same as the cast rule, but it's a saying, funny saying, that would help you to remember where the A, S, T, and C go, because that one would start in quadrant 1 as opposed to cast, which starts in quadrant 4, but it's the same letters. So the A means that all ratios are positive in quadrant 1. The S means that only the sine ratio is positive in quadrant 2. The T means that only tangent is positive in quadrant 3. And the C means that only the cosine ratio is positive in quadrant 4. Okay? So here in the previous example, we were looking at only the sine, cosine, and tangent ratios for angle beta, which is the related acute. But if we wanted to now look at what are the sine, cosine, and tangent ratios for theta, okay, the sine, cosine, and tangent ratios for angle theta are going to be the exact same as beta, except we're going to apply the cast rule in order to figure out whether each one is positive or negative. Okay, so sine theta will be y over r, just like sine beta. Cosine theta will be x over r. Tangent theta will be y over x, except in addition to these ratios, we're going to use the cast rule to figure out whether each one is positive or negative. All right, the next example, given the point P, -1 root 3, on the terminal arm of an angle theta, determine the primary trigonometric ratios. Now, -1 root 3, the x value is negative and the y value is positive, which means we're in quadrant 2. So here's the point P. Okay. We can drop in a vertical line here to make a right angle triangle. And so because of my x and y values here, I know that the length of this base of the triangle is 1, and the height of this triangle is root 3. Okay. This will be the radius of the circle if we were to rotate point P around the origin. Okay. Our angle in standard position is this one, rotated from the positive x-axis, and we've got a related acute angle that's here. So the first thing we might want to do is try and figure out what r is, because that will help us definitely to determine the trig ratios. So in order to find r, we know that r squared is equal to x squared plus y squared. So 1 squared plus root 3 squared. So r squared is equal to 1 plus 3, which means that r is equal to the square root of 4, which is 2. We know we're dealing with a positive here, so -2 isn't a possibility. So r is equal to 2. We now want the sine, cosine, and tangent ratios So the sine ratio for our angle theta is going to be y over r. So we know y is root 3 and r is 2. Now, because we're in quadrant 2, that means that only the sine ratio is positive. So the other two ratios will be negative, but the sine ratio will be positive. So it's just going to be root 3 over 2. The cosine ratio for theta is going to be x over r, so 1 over 2. Okay? But we know because only sine is positive, the cosine ratio has to be negative. And the tangent ratio for angle theta is y over x, so root 3 over 1, which is just root 3. And again, because only sine is positive, the tangent ratio has to be negative for quadrant 2. So for our angle theta, for this particular point P, the primary trig ratios are here. Okay, last example. We're going to determine the exact primary trig ratio for cosine of 2 pi by 3. Okay. Now, first of all, we might want to figure out where 2 pi by 3 is located on our Cartesian plane. Okay, so let's look at the pi by 3 part first. So that means we want to take pi and split it into 3 sections. So if I do that, I get something like this. So first section, and then the second section in between here, and then the third section, because I know that this is pi. So 2 pi by 3 would mean rotating through 2 of those 3 sections, right? 2/3 of pi. So this is the angle 2 pi by 3. We've got our cast rule as a reminder so that when we find our trig ratio, we know which ones are positive. Now in quadrant 2, we're looking at only the sine ratio being positive. Okay, so here's our terminal arm. Okay. Now we can also figure out our related acute angle. So because this is 2 pi by 3, and we need to add up to pi to get to here, this one would have to be pi by 3. So now, cosine of 2 pi by 3, this is the ratio that we want to find. Okay. Well, we know that this has to be the same as the cosine ratio for the related acute angle, which is pi by 3. Okay, so those ratios will be the same, except in quadrant 2, the cosine ratio will be negative. So it's going to be equal to negative whatever the cosine ratio is for the related acute angle. Okay. Now for pi by 3, we actually have a special triangle for this. And if you refer to your special triangle on your handout, you'll discover that pi by 3, the cosine ratio for that angle is equal to 1/2. And then we know because we're in quadrant 2 that that's going to be negative. So the cosine ratio for 2 pi by 3 is equal to negative 1/2. There is a part B question. See if you can try that one on your own, and we'll take that one up in class later.